So hello everyone. So this is the third question of control system based on the root locus plot, and here it is given that the root locus of this open loop transfer function, that is ks plus 3 upon s square minus s minus 2, it is forming a circle. So we have to calculate the center and radius of that circle. So let's have a detailed discussion of this problem. So first of all, as we can see that there's 1 0 minus 3, and the roots of this polynomial will give the poles. So there are two poles. So poles are greater than zeros. It means it is a proper transfer function. Now second is the branches of this root locus plot. So whenever the poles are greater than zeros, branches is simply equals to poles. So there are two branches in the root locus plot of this OLTF. Third is the asymptote. So asymptotes is equals to p minus z whenever poles are greater than zero. So there is one asymptote, and it means there will be one virtual zero. Now the angle of asymptote, whenever there is a single asymptote, the angle is 180 degree, and it is calculated according to this formula 2 alpha plus 1 into 180 degree upon p minus z, and here the value of alpha goes from 0 1 2 up to p minus z minus 1. So it means the maximum value of alpha is p minus z minus 1, which we can see here. In this case it is 0. So when we put alpha equal to 0 here, so we will get this angle, that is 180 degree. Now the centroid, from where the asymptote lines originate, so it is defined as the summation of real part of poles minus summation of real part of zeros upon p minus z. So first of all, we have to calculate the poles, which are the roots of this polynomial s square minus s minus 2 is equals to 0. So simply we can apply the middle term splitting here, s square minus 2s plus s minus of 2, that is equals to 0. So s is common, s minus 2, then 1 common, s minus of 2. So one pole is lying at minus 1 and the other pole is lying at plus 2, and the 1 0 is lying at minus of 3. So these are the real pole and 0. So the centroid will be summation of real part of pole. So minus 1 plus of 2, then minus of this minus 3, and upon p minus z is 1. So the centroid is lying at 4. Now we can draw the pole 0 plot of this OLTF. So it will be like this. This j omega, this is sigma, then this one pole is lying at plus 2, the other pole is lying at minus 1, and the 0 is lying at minus 3. And the one virtual 0 that is lying at the angle 180 degree means across this 180 degree line. So it will be lying something like here. This is the virtual 0, and the angle of this virtual 0 is 180 degree, and the value of k at 0 is infinite, and pole is 0. Now between these two poles there will be lying a breakaway point, and it is a valid breakaway point because the sum of the poles and zeros to the right hand side of this point is an odd number. Similarly, between these two zeros, this is a physical 0, this is a virtual 0. So there will be lying a break-in point, and which will also be a valid break-in point because the sum you can see here, it is an odd number. Now the root locus always starts from open loop poles, means it will start here from one branch will start like this, and the other branch will start like here, and they will meet at this breakaway point जहाँ पर भी इस रेंज में breakaway point lie कर रहा होगा, and one branch will go like this following a circular path and merge in this 0, and the other branch will merge in this virtual 0. So this will how the root locus will look like. So first of all, let's calculate the value of this break away point and break-in point. So the procedure for that is breakpoint. The first step is the characteristic equation, that is 1 plus GHS is equals to 0. So 1 plus k s plus 3 upon s square minus of s minus of 2 is equal to 0. So it will be s square minus s minus of 2 plus of k and s plus 3 equal to 0. Now we have to evaluate the value of k in terms of this s terms. So it will be simply k is equals to this whole term will shift to the right hand side with the negative sign. So s square minus s minus of 2, and this is in the divide upon s plus 3. So this is the value of k in terms of this is. Now second step is we have to differentiate this k in terms of with respect to s and equate it to 0. So when we differentiate according to u by v division rule, so s plus 3 whole square minus sign will be as it is, and s plus 3 as it is, and this differentiation is 2s minus 1, then minus of s square minus of s minus of 2 as it is, and s plus 3 differentiation is 1. Now when we equate it to 0, so this term will vanish out and this negative sign has no meaning here, and this 2s square and minus s plus 6s minus 3, 2s square minus s plus 6s minus of 3, and this term also shift to the right hand side as this s square minus s minus 2. So this s will cancel out, and here this is the s square then plus 6s and minus 1 equal to 0. So this is the equation we have got, and now there is no chance of middle term splitting as we can see. So the roots will be simply minus b plus minus b squared, that is 36 minus 4ac, so it is plus 4 under root divided by 2. So this is now 36 plus 40, so 40 can be written like this, 4 into 10, and this will come out of the root as 2. So it will be minus 6 plus minus 2 under root of 10 divided by 2. This one, और यहाँ पर first root will be plus minus 3 plus under root of 10, and under root of 10, the value of under root of 10 is 3.162. So the first root will be this, and the second root will be minus 3 and minus of 3.162. So this value will be 0.162, and this is the breakaway point. This is the breakaway point, and this value will be minus 6.162, and this is the break in point. So these two values are of the breakaway and breaking point. Now let's calculate the value of this k at breakaway point and break in point. So first k at breakaway point, which is 0.162. So we have to simply substitute this value in this at the place of s. So it is minus sign and 0.162 whole square and minus of 0.162 and minus 2 upon 0.162 plus of 3, and this value is coming as 0.675, and now the value of k at break in point, which is equals to minus 6.162. So again minus 6.162 whole square, then this minus sign and this minus sign will be plus 6.162, then minus of 2 upon minus 6.162 plus of 3, so it is coming as 13.324. So these are the value of k at breakaway and breaking point. Now we can draw the root locus of this OLTF. So this is j omega, this is sigma. One pole is lying at here, that is 2, and one pole is lying something here, that is minus 1, and 0 is lying at here minus of 3. Now the यहाँ पर कहीं break away point lie कर रहा है, this is the point, we can write like this, 0.162 is the breakaway point, and the value of k at breakaway point is breakaway point is 0.675 and फिर इसके बाद यहाँ पर this is the virtual zero we can make like this यहाँ पर this is the virtual zero and let's make this point here only. So this is the break-in point which is minus of 6.162 and the value of k at break-in point is 13.324. So at zeros the value of k is equal to infinite, k is equal to infinite, and here the value of k is equal to 0, is equal to 0. Now root of branches starts from the open loop code. So this is the first branch which will start like this, and now the second branch will start like this. Yeah, so this is the second branch, and now they will follow a circular path. The first branch will move according to this path, and the second branch will move according to this path, and forming a circle. So let's make a circle first, and they will meet at this break-in point. So the circle will look like this. Yes, it is a perfect. So this red color branch, which will move like this, and it will merge. Now we can merge it to any of the zeros. So let's say I'm merging it to this zero. So this yellow will merge it to this virtual zero. So this, so let's see how say this will merge into this virtual zero, and this is the 180-degree line. Now, though, so this is the circle. Now we have to calculate the center and radius. So first of all, we have to calculate the diameter of this circle, which is simply the distance between these 2 points, 0.162 minus 6.162. So the diameter will be this distance between these 2 points. This is the diameter. This is the diameter, which is equals to, so 0.162 and minus and again minus, so it will be plus. So 6.162 and this value is coming as 6.324. So this is the diameter. So we have got the diameter as 6.324. So according to this, the radius of the circle will be equals to half of the diameter. It is 3.162. So this is the radius, and center we can calculate by subtracting this value from this value, right? यहाँ से इसको subtract करेंगे, so we got the center. Radius को subtract करने से, so we can clearly see that the center is minus of 3. 1.162 minus of 3.162, so it will be simply minus of 3. So means this 0 is nothing but the center, but it is not looking like this center, so I should draw it here. Yes, here. So this is the center. Now ignore this distance, and it's the and draw there. So this is the circle with a radius 3 point. So circle with a radius 3.162. So radius is equals to 3.162. And the value of k here we have got. So now what can be the other discussion on this problem? So we can calculate these two roots which are lying on the imaginary axis, and imaginary axis when the roots are on imaginary axis means the system is marginally stable. So basically these roots are the roots of the auxiliary equation. These are the roots of auxiliary equation. So we can calculate these roots. So first of all, the characteristic equation, that is 1 plus GHS equal to 0. So it is 1 plus KS plus 3 upon S square minus S minus 2. And whenever the roots lie on the imaginary axis means यहाँ पर ROZ occur कर रहा है. There is existing ROZ, that is the row of zeros. So we will calculate like this: S square minus S minus of 2 and plus of this is KS plus of 3K equal to 0. So it will be S square and plus K minus 1 of S plus of 3K minus of 2, that is equal to 0. Now for ROZ we will apply the RS table here. So route Hilbert's tables are S square S is to power 1 S is to power 0, then यहाँ पर this is 1, then this coefficient 3k minus of 2, then this coefficient that is k minus 1 0, and this is 3k minus 2. So ROZ always occurs at the odd power of s raised to power odd में ही ROZ अगर होता है. So this is the ROZ, and for ROZ the row should be 0, so this term should be 0. So k minus 1 is equals to 0. So and this is nothing but the value of k marginal because it is lying on the imaginary axis. So k marginal is 1, and this is the auxiliary equation. just जो ROZ के just एक पावर हायर जो इक्वेशन होता है which is it is the auxiliary equation. So auxiliary equation is यहाँ पर auxiliary equation is s square plus of 3k minus of 2 is equal to 0. Now we'll put this value of k here to get the value of the root. So plus 3 into 1 minus of 2 is equal to 0. So s square, as you can see, that minus 1. So it's clear that it is plus minus of j1. So these are the roots, imaginary axis roots. So this value is j1 and this value is minus of j1. Now as we can see, these are the closed loop transfer function poles. So they are lying at the varying locations. That as we can see, there's this in this range from k is equal to 0 to this value, that is 0.675. So in this range, यहाँ से लेकर ये मतलब ये वाला range और ये basically है. So these are the overdamp poles, because overdamp poles are the real and unequal roots. So these are the overdamp poles, and from this value, that is 0.675, to at this we have calculated the k marginal is equals to 1. So means the value of k from 0.675 to 1. So these are the complex conjugate poles, and but on the right hand side of the S plane. So this represent the negative underdamped systems. Then from यहाँ से लेकर, that is the value of k is equals to 1 to is at this value, that is 13.324. These are the complex conjugate poles, again complex conjugate poles, but on the negative side of S plane, which represents the underdamped system, which is a stable. This system is representing unstable system because the roots are lying on the right hand side of S plane. So we can have a discussion on the damping also. So let's make a table for this. So the for different values of k, what is the nature of damping and the stability according to that stability of CLTF actually, because the roots are the CLTF roots. So this is the range of k, and here the nature of damping, and here the stability of CLTF. So first of all, the first range is this, that is 0 to 0.675, that is the breakaway point. So here it is now actually if we see carefully, so यहाँ पर तो सिर्फ इतने रूट्स की बात की जाए तो ये तो नेगेटिव में लाई कर रहे हैं. सो ये स्टेबल बोल सकते हैं, बट यहाँ पर कुछ रूट्स बिकॉज पॉजिटिव राइट हैंड साइड ऑफ एस प्लेन लाई कर रहे हैं, सो ओवरऑल ये बेसिकली अनस्टेबल ही है। सो यहाँ पर नेगेटिव ओवरडैम्प भी कहना सही नहीं रहेगा, सो वी कैन सिंपली से इट ओवरडैम्प, बट इट इज अनस्टेबल सीरियसली बिकॉज यहाँ पर एक भी रूट अगर राइट हैंड साइड लाई करता है तो ऑब्वियसली इट विल मेक द सिस्टम अनस्टेबल, सो दैट्स व्हाई it is actually the combination of positive overdam and negative overdam, so that's why I have said just overdam. So and now second, at this point, at this breakaway point, the roots will meet. So यहाँ पर because ये second order equation है, so यहाँ पर repeated poles होंगे, but यहाँ पर because ये repeated poles जो होते हैं equal and repeated poles वो रिप्रेजेंट करते हैं क्रिटिकल डैम सिस्टम, बट यहाँ पर बिकॉज राइट हैंड साइड ऑफ एस प्लेन है, सो इट विल बी रिप्रेजेंटिंग द नेगेटिव क्रिटिकल डैम. सो एट k is equals to 0.675, which is the k at breakaway point, it is representing negative critically dam, and here zeta value is -1, and यहाँ पर this is also the unstable. Now from this value, that is 0.6 0.675 से विर्धन, एंड यहाँ पर इस रेंज में, इन दिस रेंज, यहाँ से लेकर इस रेंज में बेसिकली कॉम्प्लेक्स कॉन्जुगेट पोल्स है, बट ऑन द राइट हैंड साइड ऑफ एस प्लेन, सो ये मार्जिनल है बेसिकली, इट इज 1. इट रिप्रेजेंट द negative under damping, and it is also unstable. Now at k is equals to k marginal, which is equals to 1. So this represents a marginally stable system because imaginary axis root. So now this is stable. Now अब स्टेबिलिटी वाली रेंजेस स्टार्ट हो जाएगी, फिर यहाँ से लेकर इस रेंज तक, ये पूरा जो रेंज है यहाँ से लेकर इस रेंज तक, दैट इज फ्रॉम k marginal to this value, k breaking point. So 1 say greater than but less than 13.324. This is the underdam complex conjugate poles on the negative side of on the left hand side of S plane, so which represents a stable system. Now at this break-in point, again the roots are meeting here, so k at break-in point, which is 13.324, so it is representing a critically damped system, which is also a stable system. And the final range is the when 13.324 say greater than but less than this range यहाँ से और यहाँ तक, ये this is the overdamped, and this is representing the stable CLD. So these are the damping nature. So पूरे कंट्रोल सिस्टम में बेसिकली यही 7 टाइप्स की डैम्पिंग एग्जिस्ट करती है, एंड these all dampings are existing in this single question, as you can see, क्योंकि यहाँ से राइट हैंड साइड भी लाई कर रहे हैं रूट्स, फिर ये इतनी सारी रेंजेस है, so that's why. So that was the discussion of this question. So okay, thank you.